is we're going to take this roll of tape. I'm going to put the roll of tape on the floor, and then I'm going to kick the roll of tape. Please observe. We're going to analyze this situation. I'll do it one more time so we can make sure we understand. The roll of tape is sitting right here, and I'm going to kick the roll of tape, and I'm going to give you various information. We're going to analyze the situation. I kick the roll of tape. It's going to slide to a stop. So here we go. The information we know in this example problem. The tape slides to a stop. We know the mass of the tape. It is 470 grams. We know the initial velocity of the tape. It is negative 4.5 meters per second. The initial velocity of the tape, negative 4.5 meters per second. Victoria, why is the initial velocity negative? It's okay, help her out. Who can help her out? Why is the initial velocity negative? Emily, Catherine.
Because it's moving in a negative direction.
It only has to do with the direction. It's to the left, which is a negative direction. So the initial velocity is negative 4.5 meters per second because it's moving to the left. The force of friction in this particular case is 1.4 newtons. As I talked about last time, I haven't really defined friction yet, so I'm not going to talk about how I got that number. It doesn't really matter at this point. We're going to push off discussing specifics about friction until a little bit later. So that is the information we know, and what we're trying to find is the displacement in the x direction of the roll of tape. So I kick the roll of tape, it slides to a stop. We have the mass, 470 grams, the initial velocity in the x direction of negative 4.5 meters per second, and the force of friction, 1.4 newtons. We're looking for the displacement in the x direction of the roll of tape. Who has a general strategy of what we should do next? Matt.
Free body diagram.
A free body diagram. Clearly this problem has forces in it, so we should draw a free body diagram. Now, the free body diagram we are going to draw is the forces acting on the roll of tape while it is sliding to a stop, as it says in the problem. So we have our forces. As we went through last time, we have all sorts of forces we could have. Bless you. Please give me a force in our free body diagram. Christy.
The force of friction.
Which direction?
Left.
Well, remember the object was sliding to your right. So what direction is the friction going to be?
Right.
To the right. So the force of friction is going to be to your right. Other forces in our free body diagram, chats.
Force of gravity.
Direction?
Down.
Down. Force of gravity, which is down. Give me another force in our free body diagram, Eric.
Force.
What direction?
Up.
How do we know the normal force is up? In other words, what do we know that defines the direction of the force normal? Tom?
It's always perpendicular to the surface, and it's a push.
It's always a push and perpendicular to the surface. So perpendicular to the surface and a push right now is this. What other forces do we have? Stuart?
The force applied.
Which direction?
Left.
To the left. This is the most common of the free body diagrams that I get at this point, and it is important to understand that this is actually incorrect for the free body diagram for the forces that are acting on the roll of tape as it's sliding to a stop. It's very important to understand that one of these forces is not in the free body diagram. Who can tell me which one it is? Sam.
It's the force applied.
The force applied is actually not in the free body diagram. And let's talk about exactly why that is. The key here is to understand that first off, the force applied is a contact force. And that force is applied, I agree, I kick the roll of tape. Everyone agrees with that, right? So I apply a force to the roll of tape when I kick it. But when I kick the roll of tape, I give it an initial velocity of 4.5 meters per second to the left. After that, it is sliding and my foot is not touching it because that's a contact force, so I'm not applying a force. In order for the applied force to be in this free body diagram, which is while this roll of tape is sliding to a stop, I would have to look like this. Did I do that? No. Okay. Because the force applied is a contact force. So the force applied is not in our free body diagram. Now that we've drawn our free body diagram, we are going to use Newton's second law. we're going to sum the forces. We're going to pick a direction, sum the forces in the x direction. Please tell me, looking at the free body diagram, Tristan, what forces are acting in the x direction, and are they positive or negative?
The force of friction is positive?
Anything else?
No.
No. Notice the normal force of gravity are both in the y direction. They may be in the free body diagram if they are not in the x direction. This is equal to, according to Newton's second law, mass times acceleration. What am I missing on the acceleration here? Check. It's not actually the vector symbol, but rather the direction. Right? The direction, so it has to do with the vector. So what am I missing here? Matt?
It's the acceleration in the x direction.
In the x direction, so it's identifying the specific direction. Because if it's the net force in the x direction, then this is the acceleration in the x direction. So we could solve for the acceleration in the x direction. It's going to be equal to the force of friction divided by the mass. Please give me the numbers here for the force of friction and the mass. Julia?
The force of friction is 1.4,
Divided by the mass?
and the mass is 470.
407. So we can figure out the acceleration in the x direction.
Should the 470 be in kilograms?
That's a good question. Should the 470 grams be in kilograms? The answer may be yes, but why? George?
Because the unit kilograms is in newtons, so one goes to cancel.
Because the force of friction is in newtons, and a newton is kilograms times meters per second squared, so we need to have the similar one. So we need to have kilograms for mass, because the force of friction in newtons is kilograms per meter times meters per second squared. So we need to convert 1,000 grams on the bottom, 1 kilogram on the top. Grams cancel out. We get 0.470 kilograms, so 0.470. So the acceleration in the x direction is
2.9787234.
that's plenty. Meters per second squared. We now have the acceleration in the x direction. What is our general approach now to finding the displacement in the x direction? Andrew?
Can you read that, please?
Sure. We're trying to figure out the displacement in the x direction. So far, we've figured out the acceleration in the x direction. What is our general strategy now to figure out the displacement in the x direction? He's not seeing it. Who can help him out? He's not seeing it. We've got a lot of the same bus drivers. Good. We're getting some others. Always good. Aaron?
Use a UAM equation.
What is it about what's on the board right now, Andrew, that says we can use a UAM equation?
The acceleration is constant.
The acceleration equals a number, which tells us the acceleration is a constant. So we could use our UAM equations. We could see we have acceleration, the velocity initial in the x direction. We also need one more of our UAM variables so that we can have 3. You can tell me what that third UAM variable is. Sam?
Velocity final is 0.
You know this because?
We're coming to a stop.
It says we come to a stop, so the velocity final in the x direction is 0. We come to a stop. Great. All we need now is a UAM equation so we can solve for delta x. When you have it, please give it to me, whoever finds it.
Velocity final squared.
I'm going to do velocity final in the x direction squared.
Oh yeah, sorry.
That's okay.
Equals velocity initial in the x direction squared plus 2 times a in the x direction squared times delta x.
I believe you put a squared on the acceleration.
I did?
Yeah.
Oh, I didn't mean to.
It's okay. So the velocity final is 0, which we're going to square. The initial velocity is negative 4.5, which you're going to square. It's important to make sure that your parentheses are around and include that negative. Plus 2 times the acceleration in the x direction, which we got from 2.9787723 times the displacement in the x direction. Therefore, the displacement in the x direction equals, bringing the negative 4.5 quantity squared over to the other side, a negative of negative 4.5 squared. Divided by 2 times 2.9787723. Yep.
3.3991 meters.
With sig figs, 3.4 meters.
Negative.
And it's negative, right? We have a negative times a negative squared, so that ends up being negative. So we have a displacement in the x direction of negative 3.4 meters. Why, qui, is the displacement negative? Because it's moving to the left. That's all it means. The displacement is negative because it's moving to the left. Class, is the roll of tape speeding up or slowing down? Slowing down. Then who can explain to me why it is we have a positive acceleration? If the object is slowing down, how can we have a positive acceleration? Sam.
It's because of the direction on the acceleration. That's all the positive and negative means.
That's all it means, I agree. So what's the direction on the acceleration?
It's opposite to whichever way we're going.
Correct. So notice the acceleration, if you're slowing down, is opposite the direction of the velocity. Let's look at the way we would normally look at this. Normally you have a velocity which is positive. If you're slowing down, that gives you a negative acceleration, right? Which is to your left. Because the acceleration in order to slow down needs to be opposite the direction of the velocity. In this particular case, we have a velocity which is to the left, which is negative. The acceleration in order to slow down needs to be opposite that direction, which is actually going to be a positive acceleration. So it's a bit unusual, but we have a positive acceleration which is actually slowing down the object because the object is moving in a negative direction.